All right, so now after adding 0.05 moles of a strong base, namely hydroxide. Now the important thing is to remember that this type of problem is actually two steps. One is the stoichiometry of the strong base weak acid reaction, and then the other one is an equilibrium problem. So we kind of need to tackle these one at a time. So at all points during one of these problems, it's really important to understand what the reaction is that you care about. So the first step is a stoichiometric step. In this case, it's going to be the reaction of the strong base that we added with the strongest available acid, which in this case is going to be the lactic acid, which I'll still continue to just abbreviate HLAC. And that is going to form water and the conjugate base lactate. Now what follows here is, I like to call this a reaction table. So it's not actually an equilibrium table, but it's useful to set up some of these quantities here. And let's see, so I've got the reaction here, and I like to split this up into a couple of points during the reaction. This is an easy way to figure out what the numbers are here. All right, so here we're looking at the concentrations that we've got before anything really has been added. So we're going to draw a line here to, if we keep things separate here. And we had no hydroxide. We said that the lactic acid concentration was 0.25 molar. The water concentration, we can kind of ignore the water here. And the lactate concentration was 0.5 molar. Now here is the numbers after the base has been added, but before it reacts. Now this is hypothetical because the reaction pretty much starts instantly, but we can start here. So we've added 0.0500 moles of this. And now these here are unchanged. 0.25 molar and 0.5 molar. Now the change you expect is the next item here. Assuming complete reaction with the hydroxide. So you expect to lose all of this because there's less of it than the lactic acid, but you expect to lose the same amount of lactic acid in the 0.05 moles, which means that you're going to gain .05 moles of that stuff too. And then the final entry is just after the reaction, which is just basically these two, the sum of these two. So after this particular reaction is done, we have no hydroxide left, and we will have .2 molar lactic acid left, and we will have 0.55 molar lactate left. So this is the stoichiometric part of the problem that we have just finished. And now we need to consider what the pH is going to be. And it's important to note that that is actually a different reaction, because the substance that is going to determine the pH of this system is actually the lactic acid and its reaction with the water. And because lactic acid is a weak acid, that system needs to be taken and needs to be treated as an equilibrium system, which we will do on the next slide. Okay, so now remember that we are now looking at a different reaction. And that is, again, the system that kind of determines the pH of this buffer is the reaction of the lactic acid with water to form hydronium and lactate. Now, this is an equilibrium system, so you construct an ice table just like you have been doing past couple weeks now, except the initial conditions that we're working with here are actually going to be the end concentrations from the stoichiometric part of this process from the last slide, which means at this point our initial lactic acid concentration is 0.2 molar. Again, water we can safely just ignore. We're going to say that we initially have no hydronium, and the initial lactate concentration here was half molar. So what's the change? Well, you can assume some forward progress as this reaction is written, because we have no hydronium to start with. You will form an equal amount of lactate and lose that same amount of lactic acid, which gives us at equilibrium 0.2 minus x mole and 0.5 minus x mole of lactate. And again, just set up the equilibrium constant expression here. So Ka is going to be the equilibrium hydronium concentration times the equilibrium lactate concentration divided by the equilibrium lactic acid concentration. And just plug in numbers here. So this is going to be x. This is 0.5. I'm sorry, 0.55 minus x. Actually, I'm going to fix that. 2 spots. And on the bottom here, we've got 0.2 minus x. Now, this is barely within the bounds, but we can probably get away with saying that this is probably equal to x times 0.55 divided by 0.2 and that's going to be, all right, I should stop with that. So our goal was the pH, and that is related to the hydronium concentration, which is going to be equal to pKa times lactic acid concentration over the lactate concentration. And here I'm going to use our approximate concentrations here. I'm not going to do I'm not going to write that over again. So the lactic acid concentration is 0.2 minus x, but we can really just call that 0.2, and divided by technically 0.55 minus x, but we can approximate it to just 0.55, and that gives us a final hydronium concentration of 5.1 times 10 to the negative 5, and that gives us a pH of 4.29. Now, note that this pH went up a little bit from the original .15. It went up, which is a reasonable answer, given that we actually added a base to it, so you'd expect the pH to go up. Now, you might ask, why did I not just use the Henderson-Hasselbalch equation? And why did I not just say pH equals pKa plus log of the lactate concentration divided by the lactic acid concentration? And we could have done that, and that would have given us pKa is 3.85 plus the log of .55 over 0.20, which also gives us 4.29. So what we did is exactly the same thing. I did it the long way first, just to show you or to remind you again of where that Henderson-Hasselbalch equation actually came from. But these are in fact the same thing. And props if anyone actually caught my algebra error. Actually, good. Nope, that's right. All right, so either one of these should actually give you 4.29. So again, the Henderson-Hasselbalch equation is appropriate whenever you have non-negligible amounts of both the conjugate acid and the conjugate base. You just have to be sure you're in that range, and know that that's just, the way that these equilibrium tables will always tend to pretty much look the way that there is, and that's why we end up with one general equation, the Henderson-Hasselbalch equation, that works under these conditions. Either one's fine. Right, next step, adding acid. Okay, I lied. I want to do one more thing with the base, and that is so talk about with the pH change. If you add that same amount of base, that half mole, to 1 liter of water, so which is the same thing. We're as we did with the buffer. And note that pure water at 25 degrees Celsius has a pH of 7.0. So we can quickly calculate the hydronium concentration by using the autoionization of water expression. So that's just going to be equal to Kw divided by the hydroxide concentration that we know. And that's 1 times 10 to the negative 14 divided by this 0.0500, which gives us a molar, which gives us a hydronium concentration of about 2 times 10 to the negative 13 molar. That there is an extra sig fig. So the pH in this case ends up being 12.7. So this it went up by 5.7 pH units. Contrast that with the buffer, which went from the buffer went to 4.29, pH of 4.29, and it started at a pH of 4.15, which is, if my math is correct here, a 0.14 pH unit change. Now that's not nothing, but it is a significant difference. So in this case, this more or less represents a change of about a little more than 100,000. So the amount of hydronium, the addition of pure hydroxide to this system was muted by a factor of over 100,000, pretty close to 500,000 in this buffer system relative to pure water. So it is not immune to pH changes, but they are severely dampened. All right, now we'll add acid.